Thank you. Good afternoon, everybody. I know I'm standing in the way between you and the gala dinner, but I'll make sure this is as interesting as I can make it. So today I'll share a little bit about my work on a flexible screen printed antenna for the 5G n260 band. Okay. And just a quick overview of the presentation. I'll start with a quick background about the work and why this is of interest. Then we'll dive into the design and fabrication details with some of the results that are, constructing these wireless devices. In this case, particular antenna. And then we'll have a quick summary and some outlook for future works. And then at the end, we'll open up the floor for questions. Quick background, I'm affiliated with Material Science Engineering Department at the University of Washington and also Washington Clean Energy Test Beds in Seattle. We have a multitude of additive manufacturing equipment, which is particularly beneficial for flexible electronics. Just because of the wide variety of techniques we have to make our devices, such as inkjet printer, going from piezo, aerosol, micro dispensing, and EHD to something that's a little more commercial and large format, which sheet to sheet and roll to roll printers. My specific research is focused on structures, including high density interconnects, and also antennas and arrays, which I'll share a little bit more about. That are additive manufactured and flexible. Others include rectenna, high density packaging, etc. Summer is a great time to come to Seattle. Overall, besides that, you probably shouldn't come because it just rains a lot and a lot. So here are some of the print systems we have at the test beds. We are an open access facility, which means anybody can come in, visit, and use our machines if you want. You're more than happy to do it. Some of the nozzle-based printing systems we have here are N-Script printer, EHD system by SIJ, which are exhibitors in this particular conference. So some of the work we'll be showing is actually printed by exactly the exhibitor we have here. And then some XTPL micro dispensing systems, state-of-the-art, just brand new, and some more larger format print systems, which is sheet coder, screen printer, which is what I use in this particular case for a lot of the manufacturing, and also a really room-size R2R printer, which is more for commercial applications. Okay, so the research motivation is that as frequency of operation goes from 2.4, 5.8, all the way up to 60 gigahertz for 5G and up to hundreds of gigahertz for 6G, antenna manufacturing becomes more difficult. This is not only for rigid, but also for flexible substrates. Obviously, there are still options such as polyimide or LCP, liquid crystal polymers. However, the options become much more limited as you're going higher and higher frequency. Typical PCB manufacturing, which is 75 micron, 3mm capable, does not really have the sufficient resolution to support the terahertz structures that we're looking for. For example, 1 terahertz free space wavelength is 300 micron. So if you're fabricating something with a 75 micron resolution, that's a quarter lambda, and good luck with making anything useful or consistent. Also, organic flip chip packaging, which is 15 micron capable, or RDL technology, which Singapore has a lot of hubs, IME for example, that are focusing in advanced packaging. They are really typically high in cost, have lengthy turnaround time, and not environmental friendly. We partner with our industry partner. These are standard PCBs made by NFR and also organic substrate by NFR, which features 15 micron resolution. However, we understand that this is not really sustainable for research and development uses. So now overall is that, okay, so how do we look to address this? The way that we're looking to address this is by additive manufacturing. We're looking to achieve not only high resolution, but also high performance interconnects and structures to support next generation protocols for a wide range of applications. For example, 6G, which is rumored to be going up to 300 gigahertz plus, AR, VR for headsets and whatnot, and then also for mobile headsets such as your cell phones and etc. Here is a quick overview of our research. Starting from 2023 Q2, we were Semicon West. This is a wireless flexible device. It's a 2.4 gigahertz rectenna. It's an antenna with an RFIC integrated on the flexible ceramic we have here, and then there's no power source at all, and it is receiving power wirelessly to power up the LED that's green right here. And then following that, in the same year, we did some more rigid based work where we're doing more on the phase array application, where we do a 3x1 array as you can see from the green, from the black to the blue, is that we get an improvement in the directivity as we increase the number of elements. Now, as we transition to last year, 2024, what we have is that going from 2.4, we go to 3.5 gigahertz, and we're going higher and higher frequency. At 5.8 gigahertz, Rectenna was published at a WPTCE Wireless Power Transfer Conference, and over 200 millimeter over-the-air wireless power transfer was shown. And this, again, this is a lovely green LED that we can see, and this is shown when the device is flexible and conformal to a curved surface. And then the TXI is 1 watt FCC regulatory. So this is just a standard. Any mobile headset or any kind of router you use, you can actually just put it right next to it and it will light up. And then just recently, the publication finally got published by JFlex. Just going through the review process is 24 gigahertz antennas, and these specifically one I want to highlight is flexible ceramics. So this is flexible alumina, which is one of the kind in the world. And then we're actually coupling this with a copper-based ink, which it has its plus and minuses. One of the difficulty is difficulty in processing. However, it is substantially cheaper than additive manufacturing favorite, which is silver, right? And lastly, now here we are, what we're showing today is the 40 gigahertz antenna for the n260 band. And then you can see here on the bottom that is quite flexible, and we'll have some more pictures on that later. Okay, so why was screen printing chosen as a manufacturing method? The first one is that it is actually relatively much more environmental friendly versus traditional manufacturing methods. So just a quick overview is that for making typically anything that is PCB or semiconductor based, you start with a substrate, you deposit a conformal layer of metal, and then you photoresist, and then you exposure develop, and then you etch it away. That is actually very, very wasteful in terms of energy and also material wise. So this is just printing directly where the antennas need to be. Secondly, it's sheet to sheet capable. That means that it's substantially higher throughput. So referencing the previously inkjet printed machines that I showed, this is directly one pass, and then the sheet is ready to go for next processing instead of something like an inkjet printer where you have a nozzle, and the nozzle is going back and forth to print and rasterize a pattern. Lastly, is that we have now been able to achieve very consistent high resolution in terms of screen printing to pattern these features down to 40 micron, which typical PCB manufacturing cannot meet. Now, in terms of design element, my personal favorite is the dipole antenna. There's many reasons. This is a one layer of conductor, and secondly, there's no dependence of any ground plane on the substrate. The substrate with the ground plane is going to actually come into play in terms of how small we can wrap and flex these things. And lastly, we're using copper-based inks in conjunction with polyimide substrate for cost consideration. Although we have access to flexible glass or flexible alumina and also silver inks, copper with polyimide is the typical combination that would achieve the lowest cost. Okay, in addition to some antennas, as a proof of concept, we also did some devices such as an inductor on the left and capacitor on the right to not only showcase the resolution capability of the screen printing, but also to show further integration of antenna plus passives in the future. Because for anything that's in this particular frequency to be usable, you have to integrate it with some kind of filter or some kind of passive for matching in order for it to be truly useful before it connects to our RFIC. So these are just some quick proof of concept just to show that this is also possible and to demonstrate that we can print at extremely high resolution. Okay, so the manufactured dipole antenna that was shown previously is characterized with the network analyzer. The dash is the expected is a simulated response, but clearly we can see that there's a large shift from the measurement result. The discrepancies, I would say, is expected for any RF designer. They either come from simulated and printed dimension differences just because of printing tolerances, or most likely in this case is simulated and actual material properties. Material properties are not well characterized above I would say 10 gigahertz. For Rogers or any kind of RF material, 10 gigahertz, maybe 20 gigahertz, but definitely not at 40. We are using the material properties at maybe 10 to 10 kilohertz up to 1 gigahertz to design. And this is another reason why dipole is so favorable, because we can actually tune it specifically and use it as a calibration structure to identify the material properties at the frequencies of interest. And now to address that, what we did is that we did a sweep of the dipole length going from 1650 micron all the way to 1750 micron. And as physics expects, we can see the frequency shift going from left to the right as the dipole length decreases. And as you can see on the right side here, the measured S11, we can see that it follows a similar trend, although that it does not look as pretty given that is a measurement result. Okay. And then lastly, here we can see that at the end, we're able to nail down at 1650 micron dipole length. This is actually able to encompass the 37 to 40 gigahertz n260 band. And this is what is going to enable the high bandwidth 1 to 1.5 gigahertz bandwidth at this particular frequency for the high throughput that would be needed for the 5G communication. And then on the right side, this is just a really, really large picture of what the antennas look like once we have a fixture around it to wrap it to show its flexibility. So the radius is roughly 3 millimeter. I have nothing for reference, but something like this HDMI cable is already thicker than a 3 millimeter radius. So this is quite small. And the goal is that we will be printing this in mass in a phase array format such that we are able to, beamform and also direct power wherever we want it to be. A quick summary here. Additive manufacturing provides ways to provide to rapid prototype and manufacture high resolution millimeter wave for current generation 5G protocols. A dipole antenna and arrays are designed, manufactured via screen printing, then measured to confirm the validity of screen printing as manufacturing method for by comparison of simulation and measurement results. Lastly, printing of higher frequency antennas and other RF structures to follow as future work, which I'll just quickly show here. Some really high resolution printed features by our exhibitor SIJ right here. Some RF passives on alumina, and then right here is a 2.5D printed structure. This is fully printed by a printer, and then this is a silver conductor that is 2.5D for integration. And then over here is our flexible 40 gigahertz rectangle that's currently on testing. And lastly is that we can see that there's a 60 gigahertz 20 by 20 phase array. And the goal is to be able to connect all these to RF ICs so that we are able to have beamforming applications. Thank you. Any questions?